this session will be kind of a very simple and very crisp and simple session, because the hands-on which we will be covering in the coming days, this session is a prerequisite for all those hands-ons. So again, taking into consideration, it might be repetition for some, but it might be new to some. So but to stick to the orientation of the course, we would start with this hands-on session, knowing about the databases and retrieving data, biological data. And then uh, I am I am suppose that this will definitely be a prerequisite for the upcoming hands-ons and upcoming practical exposure that we are going to uh, learn and see. So, okay, let's start our session now. So yeah, so the takeaways, hopefully, since all of you are more or less similar to the course, and from the say more or less similar to the domain, you might have some 50% of you might have a sound knowledge in or understanding, or you might know what these databases are up to. But still, again, it is for the due of the course. We will continue with this, and yeah, we'll look through different dimensions, if possible, if time permits. So yeah, so the takeaways are, you will know biological databases and file formats which are used, like not the new ones, which are used traditionally, that is, which have been existing for a long time and are a database which have bulk information and which has been growing uh, at par. So, and we'll also look at the data retrieval part and visualization part. So first and foremost of biological databases is the NCBI website, a very commonly and well-known website. So the NCBI domain, I mean the web domain, and it is used for retrieving biological information of all sorts. So well, we will fetch information. So as a hands-on practice, we will fetch information of GAL4 protein from the budding yeast Saccharomyces cerevisiae. So just to stop here, I'll take a pause here. And how I are all of you are using a system, or are you connected through your phones, mobile phones? Are you using a laptop or desktop or mobile phones? Okay, so equal contribution, mobile phones and laptops. Fine. So those who are using laptops or desktops, uh, we can have this hands-on, like hand in hand. So we all can do it together. And those who are like going through mobile phones, you can have a watch of this. Yeah, again, I say this is going to be a prerequisite hands-on course, hands-on session for the upcoming practical exposures. So please do watch, and yeah, so I think you will get to know things. So yeah, the ones who are using laptops and desktops, I would like you also to join, and like we'll start doing the hands-on side by side, hand in hand. So yeah, so let's start. We need to go to the NCBI website. Okay, so I think I have it ready. Yeah, and we are gonna search for GAL4 with all databases as the search criteria. So we are not going to select any particular database. We are going to have it as all databases, and we are going to go for our search. So this is what NCBI does. So basically, NCBI is a library of domains which can basically it's web wrappings algorithm. It works on the web wrapping algorithm. So you give your keyword, it gets you the data relative to all possible biological domains present. So we have results found in 27 databases, and the numbers are so high that we cannot sort this. You just cannot manually scroll down to each and everything, right? So what we are going to do, so yeah, so we have got the list of databases. So now we will be proceeding with the protein database, and yeah, here you get the numbers. So now this is what is the question comes here: how many results had we obtained? So we obtained around sorry guys, sorry guys. Am I audible now? Am I audible now? Yeah. Sorry for the interruption. Yeah. So, for example, I am working on want per cancer, and yeah, I'm sorry guys. I have some network issue. I suppose it's getting disconnected in between. So, am I audible? Voice is breaking. So, am I not clear? Okay, is it clear now? Yeah, if it is clear for some and not for others, then I think there is some like network lag with you also. Okay, so can we go? Can we proceed? Yeah, fine. So yeah, so we need to use keywords. So we should be aware of keywords, how and the use of keywords. So basically, as we started, we are going to look at GAL4, the budding in the Saccharomyces cerevisiae. So we are going to use Saccharomyces cerevisiae as our another keyword, and we are going to use the logical operator. So the basic algorithm behind it is using logical operators, and definitely beware, the operators are case sensitive. So you cannot go with small cases, low cases A and D, or sometimes it tends to take that as a query and not consider it as an operator. So fine. Now I think we can go with GAL4 and Saccharomyces cerevisiae as, yeah. So this will be our text of search, which is good to go here. Okay, so I hope that serves some purpose. We got our findings. So total number of items, the hits we get is narrowed down 6,902 from 2 lakhs. But still, this is also a huge sum. So now what are we going to do to still more narrow it down, still more bring it down to refine the search to get a desired output. And there we use the advanced search option where we are going to specify what is the keyword we are using. So gal4 is basically a gene, right? So I am specifying gal4 as a gene name. Also we use service Saccharomyces cerevisiae. So what is that? That is the organism, the host organism on which we are expecting the protein to be. So we go. Yeah, so good to go. And after having the builder, we have built the search accordingly, and now we are going to search with them. So now you see, like gal4 is annotated to the gene name, that is it has a property now, and Saccharomyces cerevisiae is an organism, so that is given a property. So the search is completely narrowed down and you get your search down to 296. So out of this, yeah, good to go. I'll take the first accession ID P04386.2. Well, I wanted this. So now how am I going to retrieve this? How am I going to take this particular hit, this particular item, which we have searched? So here is the basic details of this protein, and yeah, its locus is on yeast. It has 881 amino acid length, and here we use the FASTA file format. So I hope you all are aware of a FASTA file format. Yeah, good to go. We have so this is the way we like we search down, we narrow down and retrieve our protein sequence or a nucleotide sequence or whatsoever may be. So now the FASTA file format can be directly copied and it can be pasted in a notepad, and like again you can save it with the file in the file format .fasta. So that will serve the purpose. And moving on, so yeah, so what about the result? We got the improvement, right? So after doing the advanced search and all, we got the improvement, and yeah, we have got the difference. So now we got a protein entry. So as told, P04386.2 was the accession number which we were looking for. Yeah, but before that, I did not know the accession number. Maybe I was not quite sure. I just know the gene. I just know the organism. After my search conditions criteria is done, I got my result. And after saving that into FASTA format, I can further proceed to any of the operations. I can continue with a sequence alignment, or I can continue building a template for it. That we shall see later. So same way, I actually wanted, so most of you are on phone. It would have been good if you were on laptop, so I could have had an I this as a test for you guys. So like we saw NCBI, Proteomics server, the Swiss Prot server basically. Basically, it is also a good to go server. So here we are going to search for the breast cancer gene. So I think I could do that. Wow. Yeah. So BRCA1. So this is the Xpassi web server, web portal. So here we need to choose Uniprot KB and SwissProt. So because we are going to use the SwissProt as analyzed database, not directly going on the functional information, we just want the protein sequence database. So we are going to use this. And yeah, you can see this reviewed, yes, right? So basically this is under Uniprot. This SwissProt, the component of SwissProt, the complete data information of SwissProt is under Uniprot KB. And once we are opting for Uniprot, so which comes with unreviewed Tremble database computation, which is computational analysis. So when we opt for this, these two sections are activated on Uniprot KB, and we get a query say as reviewed, yes, and you can give your input query here, which will automatically be reframed once the search is done. See, it is reframed BRCA1 human and reviewed yes, and reviewed yes is the constraint, is the SwissProt constraint that is already activated. So yeah, we got around 164 hits, and the question of interest actually is, what is the accession number of the protein made by the human BRCA gene? So it is very particular. It is very particular that we need human BRCA1 gene, and it is not, but we have a lot of hits here. Fine, 164 is quite a small hit, but still you cannot be spending time manually to search which is what, right? So what is the immediate step that you would be doing? If anyone could give a suggestion in chat after seeing the screen. Yes, we can go for it. Yes, exactly. It is just the same setup. It is just the same algorithm, same ideology behind. So what is BRCA? Basically, it is the gene name. And what is human here? It is the organism of interest. Okay, the search, and we got our result. So P38398 is the answer, the accession number for the breast cancer human sequence we have been looking for, the protein sequence we have been looking for. Yeah, so that is all about Xpassi. And yeah, good to go. So yeah, next is kind of very important database for the ones who are using who are working with proteins a lot. So once those who work with proteins, or those who work with protein structures, this is kind of a logbook to all of us. Yeah, basically I'm one from the protein background, so yeah, this is one logbook for all of us. You have, okay, so basically the PDB setup is, once you get into PDB, so I am already there in PDB, I have a search, right? So fine, I'll quit back the search. I think I will be better if I just go to the home page, start afresh. Yeah, so you see the numbers, right? 168358. So these are the authorized entries in PDB, in the protein data bank. So these are all accepted, and these are all issued, these are all filed, and these are all the accepted structures of different proteins from different clinical studies, or different experiments, or different yeah, again, analysis, whatever has been done with a lot of proteins and its structures. Basically you get the X-ray crystallography structure, or the NMR structure here. So we get to know the properties of these structures. So the structures which are registered with PDB, which are available in the data bank of PDB. So these structures are from lots of different studies. So some are from neurological degenerative diseases. So there are experiments, there are studies, and there are works, project works, which are going with neurological degenerative diseases. And there are relative proteins, protein entries here. Uh, just an example, and in the same way you have for many domains, and like within many biological domains, many biological works and relative proteins and their information, structural information from PDB. So yeah, so for the hands-on purpose, we will be looking at 1HED. So I got a PDB ID here, 1HED. I have run the search. Yeah, I have got my result. So here I get a 2D representation of what it is, and you can have also have the 3D view here. So the basic details, the introductory details of any protein structure. So what this structure is all about. It's basically the consequences of hydrophilic amino acid substitutions in the hydrophobic pocket of human carbonic anhydrase 2. So it is just a very simple, in the sense, it is very particular protein. It is a very particular protein which has been identified and has been put into this repository, uh, so which deals with the just a hydrophilic amino acid substitution in a hydrophobic pocket. So all these kinds of proteins with different, they're all from different varieties. So they come from different studies. They have their background cited, where they come from, why this protein is here, why is this here in this repository. So we all can have all the, so these are the deposition authors. So these guys must have done something with this, right, to have it successfully put here. So, okay, so basically this protein is from hosted in the organism, human beings, Homo sapiens, and it is from the oxoacid classification. Yeah, so the experimental method, which method the structure was captured, the structure was looked into, X-ray diffraction. So basically it's an X-ray crystallography structure, and has a high resolution, quite high resolution, and the R value. So we all get the statistics, relative statistics of the protein, and we scrolling down, we can know the chain, number of chains. So we have this protein is a single chain protein. So this has only one chain. You can see here the macromolecule content. You can know the weight of this total structure, the atom count, the residue. Yes, true. Carbonic anhydrase is a universal enzyme that acts as a receptor to carbon dioxide. True. Unique protein chain. So there's just, it's a single chain protein, right? So you can see the residue count here is 255 and the sequence length here is 260. So what is this deviation? No, there is no mutation here. So what causes this deviation? Uh, Probably you have something else to know, that there are some ligands attached to. So there are some ligands interacting with the protein, interacting with the chain. So put together you get the sequence length. And then what else information which we get? So we get to know the unit cell information. So basically, X-ray diffraction is a clinical procedure. It's a kind of clinical procedure. Fine. So why are we reported the unit cell information? So I hope you people might be aware of molecular dynamics simulation, or uh, Monte Carlo simulation. So all these simulation studies need a virtual unit cell, right? So to proceed with the simulation, we all need. Okay, you can tell about the colors depicting the 2D structure of the molecule. Yeah, fine. We will go into it. Just we will look at the sequence and the colors which depicts things. Yeah, sure. Before that, how do we know the coding name as 1HED? Okay, that's a quite good question. So ones who don't use PDB, how will you know a PDB accession ID, right? So generally, when you work with different proteins, okay, so when you are working with different proteins and different proteins which involve, so this is basically a structure, right? So this is a structural snapshot, uh, not exactly a complete protein. So this is a structural snapshot of a protein. So in that case, you work with, whenever you work with some kind of protein involved, you can have a direct search with the name itself. You need not go with the accession code only. So for example, I would like to look at kinase. So it can be any kinase, right? I just am going with kinase. Hold on. So I have got a huge number of hits. So I got around 30,753 structures, right? So again, this total concept, as we previously saw, is based on your search. So what exactly you want. So 1HED, I just wanted to directly go into because we already have seen with NCBI and XPASI. So in PDB, it works the same. You need to be precise of what you want. Now I have just given a keyword named kinase, and I have got around 30,753 structures. Now I have to narrow down what exactly I need, right? So there are criterias. I can say I just want the structures from NMR and not XADI fraction, and it will again resolve. It will refine my search. Then I'll say like I want only Homo sapiens. It will refine my search. I can go with the taxonomy. I can go, yeah, again the experimentation method. So you have these many reported methods, and so you have a lot of search criteria. I can say I can be very particular that my resolution should be in this particular limit. Okay, sorry. So I think I'll slow down. I'll slow down. Yeah. So fine. Uh, to answer that question, why? How do we get the coding name? Yeah, you always don't get the coding name. You always don't get the coding name. You need not be aware of it, but you will be sure of what you need, right? So it is completely, any database works under that. Not only a biological database, let it be any database works under this functionality. The user knows what he needs. He can put them into words. If he doesn't know what exactly the ID belongs to, I don't know the employee ID, I can describe things, like I can describe, I want a tall fair man with wearing a big goggles. So my conditions, the attributes I'm letting in as keywords will refine my search, and at last I might find the person. So that is the whole idea behind. So 1HED is just an example to know what exactly PDB has, just not to look into the searching part again and again as we did for NCBI and XPASI. So we just wanted to go through what exactly this shows, what exactly PDB has to give us. Okay, how we find 3HQP? Yeah, so okay, I did not type 3HQP, Dr. Rupert. So, ma'am, I did not type directly 3HQP. It is, I just search for kinase. So, this is showing me around 30,753 structures of kinase, and 3HQP is one top hit, like on the first page. That is it. So, I have one TKL, I have one QK1. So, all these are not at all in relation. Like the only relationship between these structures is the organism, right? And they are like, they are from extra diffraction. They have kind of similar, more or less similar resolution. But you can see the release date. This is in 2010, and this structure was put into repository in 1998. So it is not that I am searching for a particular accession ID. Again, I'm telling that you can go with your own search. Yeah. So I think let's move on with 1HAD. So yeah, I got this. Yeah, any kinase could be fine. No, not exactly, ma'am. See, it is, again, it is, there are constraints. It is not a terminology said like, I give kinase, I can find all sort of kinase. I can find variants in all sorts of kinase, but not exactly all kinase, because because you might not have something, a structure for something which you are searching for, right? So that is why we have modeling, homology modeling. We have we need to model certain proteins. So not always you can get what you want. Maybe, yeah, if you are working with proteins, if you are working with a beaten track, or if you work generally, if, people working with cancer nowadays, there are a lot of data in cancer, so you can refer to things. uh, Per se, uh, a real time example. So I have been working in neurodegenerative diseases for the past 3 years. So uh, the amount of data which I have found for cancer as a comparative analysis, and the amount of data which I worked with neurodegenerative disease, there is a huge comparison. I was not able to find that many data with neurodegenerative diseases because the number of data which has been reported are less, and you can sort out like that. So neurodegenerative diseases as an example, there are certain other various factors, various domains for which you don't have data, that much data that has been reported. So kinase is a very regular form of terminology which has a lot of kinase proteins. There are a lot of kinase proteins which have been identified, which have been discovered through a lot of works and a lot of studies. Yeah, so moving on with 1HAD. Yeah, we look at the sequence. So just we look at the sequence. I did not miss that question also. So yeah, so this is all about the basics. So the unit cell, why do we need unit cell? I was telling about that. So yeah, so we people would be aware of molecular dynamics simulation and Monte Carlo simulation. So simulation studies are just the virtual form of any structural analysis. I just need to know all possible conformations that a protein can undergo without degrading, without breaking down into pieces. So I need to build a virtual model. For that, I need to know what is the experimental unit cell value, the length, the dimensions which has been given for them to put a protein into it. So they literally did. They literally had put a protein into the unit cell, and we cannot do it virtually. So we are when for computation analysis, we need all these data. And moving on to the sequence part, yeah, I would go sequence part. So yeah, the representation. So directly seeing through the structure, I thought I would always suggest you look through the sequence, because in structure you might not always visualize minute details. You can very well point out and say, okay, this is a helix, this is a beta sheet, but you can not be very precise unless otherwise you know the structure, you know the number in the sense you know the order of alignment. So you should be aware of sequence, and going with the sequence and going to the structure will always give you better insights and better idea. So looking at the sequence, yeah, it is a 260 260 basic, yeah, so it's a 260 amino acid length sequence. Have a Uniprot align. P0098. So there has been an alignment done through Uniprot. So this is that alignment position, alignment score. So this particular region is the mismatch, and everything else is aligned. Moving. Okay, what is Ramachandran outlier? Yeah, ma'am, I'll come back to that. I'll come back to that. I'll just get through with this and I'll come back to that. Okay. So, yeah, we were going with, yeah, so Uniprot aligned. So we got our sequence aligned in the against the Uniprot database, and we have a alignment accession ID here, and we can find there is a mismatch also. So this is a pure representation. If you want to go in detail, you can click and go in detail. Yeah, which we will not be doing now because fine, we will look into it after we complete the PDB part. And then what other details PDB has to provide you? It provides the helix. What are the regions? You found helix. So from position 13 to 18, there is a promotive. It is a helix, alpha helix. It's a promotive. And after that, you get another promotive, that is another helix from position 21 to 24. So you will be aware where are the alpha helix present in the sequence. So does you will be aware of the beta strand too. So it is another promotive, it's another super secondary structure formed. So you will be aware of the beta sheet too, and the position from where to where. So from position 39 to 40, it's a quite a small bend. So that is just how this current page opened. No, I'm not telling it's a promoter region. It's a promotive. It's not a promoter region. How this current page opened? Okay, fine. I'll show that to you. So this is what was the page after you search for 1HED. You get this page. You see sequence here, right? So you can go click the sequence to know the details about the sequence details, sequence information. Not always, not always. Alpha helix always represents promoter. No, not always. Okay, going with. Yeah, and you have the Ramachandran outlier as, yeah. So someone asked about the Ramachandran outlier. Yeah, Dr. Rupa ma'am. So you will be knowing where exactly the outlier is. I'll tell you what Ramachandran outlier is and what Ramachandran plot, what Ramachandran distribution exactly does. Why do we want to know our Ramachandran plot? So basically, we are looking at the allowed regions of a protein. So what is an allowed region? So the points where the protein can interact, there are positions where the protein will, any interaction, any vulnerable interaction can degrade or break down the protein, or any vulnerable interaction can can tend the protein to form aggregation, which again is a mutation, and is that will lead to eventually it will lead to yeah, so you can call it, you if the protein is involved in any disease, it will lead to diseases, it will tend to express diseases, it will tend to express that particular disease due to its association, vulnerable association, due to its aggregation, and all these are identified. So we should be aware before moving on to any analysis, or before moving on to any experiment with a particular protein. We should be aware like what is the exact specification of the protein. So to be, it is kind of technical. So we should know like again, we should know where are the alpha helix placed, where is the beta strand. Yeah, we should know the outliers in the sense the allowed regions, the disallowed regions. So we should be aware of the torsion angles, that is torsion angle in the sense the bend, the 4-angle bend, which is a breaking point for, which can be a breaking point for any protein. So we should be aware of all this to, so as to not avoid the aggregation or misassociation. So proteins tend to misfunction because you can always not have the protein in novel structure, right? So protein's novel structure is is a question mark unless otherwise the other parameters, the surrounding, the environment, and the conditions are good to go. So everything comes into play, and this Ramachandran outlier helps us to identify the particular regions which are allowed, which are disallowed, and of course, if at all our protein is, is tending to form aggregation, we can stop it. We can avoid that. And yeah, angle outliers. So again, the angle outlier is um, the angle between the two residues, the residues inside in the sequence. So the outliers in the sense, there is a particular ideal angle for between two residues. So there are possible formations of angles, one such as torsion angle. So there is always an ideal angle for an ideal conformation of a protein, and these outliers are such that that particular position, in that particular position, the angle formed by the bond angle formed by between the residues are either above the threshold or below the threshold. I mean, not the threshold, there is a range. Yeah, so to be precise, sorry, that is a range. So it should be within the range. So they say 1.51 for carbon-carbon interactions. Some say 1.54. Some say 1.53. So it is always in a diverse study. We do not go very deep into the bond angle. Yeah, of course. When we study in detail like simulation, we always are worried about even 0.01 degree change. Fine, but in diverse studies we do not always are worried about the bond angle, because 1.51 to 1.54 is a good to go region, but above that and below that, no, we always consider it as an outlier. We would try to eliminate that outlier. We will try to rectify that. So okay, Bhageshri sir, as a bioinformatics student, what are the softwares we should have? I am new to this. Okay, it is the softwares. Fine, it is not about exactly the softwares you use, it is about the concepts. Okay, fine. I'll tell you, you must be aware, as I told, any bioinformatics student will be dealing with data and will be dealing with information, will be dealing with analysis. So a bioinformatics student should know to visualize things. So he should Pymol is a good to go visualization software. You should be aware of VMD. So VMD, you can do your energy minimization and other concepts. You will be coming through all these concepts in your course, in your bioinformatics course. Sorry, I'm just answering a question, and if I hope some are aware of what I'm saying and some might not. So this is not with the course, this is outside the course, and I'm just trying to help her and answer her question. Yeah, so again, coming back to that, as a bioinformatics students, you will be working with a lot of tools, lot of softwares. The perks Gromacs can be used for energy minimization or protein interaction. Yeah, it is. Gromacs can be okay, fine. Gromacs is a well-known software. It's a well-known tool where you perform MD simulation, right? So you can perform MD simulation through Gromacs, and that has always been the basic understanding of any bioinformatics students. Any bioinformatics students is taught MD simulation, his first MD simulation through Gromacs, and then only he is aware of MD simulation, molecular dynamics simulation through VMD, through NAMD, energy minimization. There are a lot of stuffs. It is not that you have only these many softwares. You have lots and lots of alternatives, and particularly you have nowadays in the last 3 years, lots of people have come up with lots of servers, online tools. So you need not have standalone tool for every single operation, every single experiment or analysis you want to do. Even for a gene expression analysis, enrichment analysis, you have things online. You need not get the software GSEA, and you need not just work on heavy files, prerequisite files. You can just directly give the accession IDs. You will get the result. So things are going that fast. As a bioinformatics student, I would suggest you to dig through softwares, dig through tools. There are lots and lots of tools online which people are not aware of. If you are one such, but you always first need to know your domain. So know your domain and dig through things. You will get whatever you want. Can I use this software in my research? Is this freely available? Which software, ma'am? Can you be precise? Which software? Dr. Rupa, can you be precise? Uh, Ma'am, are you talking about PDB? Yeah, these are online databases. You can definitely use it for your research. Of course, if you find your, if you find again your required desired output, you can definitely use. You need not pay. Yeah, of course, these are freely available. You need not pay for all these. Fine. So there are a lot of information. Fine. So I would suggest all these covering all these information now is not possible, because you need to have a separate understanding. See, till angle outlier, bond outlier, since we all have been learning angles and bonds throughout our school life, we would easily relate to things. But continuing with a cis peptide or rotamer outlier or a metal coordination, a binding site Hg or zinc binding site. So these, the binding site particularly, this might vary. It will vary how we identify the unknown protein. Yeah, ma'am, you can go with the nature of the protein. So, okay, fine. First of all, unknown in the sense what? Do you you perceive that it will be existing? What are the online tools for gene expression analysis? So, for gene expression analysis, okay, what kind of analysis do you want to do? It depends. Again, I'm telling you, right? It depends. What is your exact analysis? If you want to do enrichment analysis, yeah, use this, and use this. So for beginning with enrichment analysis, these two tools, online tools, are very good. They are very good. You can understand what kind of outputs and what kind of results it is coming up with, and then you can go with standalone tools. If I extracted unknown protein lab, okay, ma'am. So you have a separate process which we will be covering on the later days, coming days. So if you have an unknown protein, first thing is you need to model structure. You need to identify whether it has a structure or not. It has a whether a reported structure is there for, or not, for the protein. You need to know the sequence. You need to align the sequence with some databases, and then you will get your hit. If it is on existing protein, you will get a hit after the alignment, and that hit will definitely lead to some of the database. Either it will lead to NCBI, it can lead to XPASI, it can directly lead to PDB. So it will definitely have an accession ID. If it is a new protein and it does not have a structure, then you can build the structure. You can very well build the structure, and after building, so that is what is all about homology modeling, which we will be seeing. So after building that structure, you will also get template proteins. So with it, I should know the amino acid sequences. Yeah, you should know, you will be knowing the amino acid sequence. Okay, now you got an unknown protein extracted in the lab, right? You can clinically identify the amino acid hits, right? So you have the codon regions. You should be aware of the codon sequences for that. So any, if you want to do gene ontology, go for David Bank. Yeah, you can go with David Bioinformatics if it is for gene and ontology. Or if you are one coding person, you love coding, you love programming, I would suggest you to learn R programming or Python programming to do gene ontology. There are a lot of codes you can work on GitHub to identify performing gene ontology through R programming or Python programming. Again, this is for those who love coding, and those who want to go good with softwares. Yeah, David is a good software. It's one good software to work with. But I would suggest for beginners, go with Imagio and WebGStore. How can we attend class for R and Python? Okay, so R and Python, you can, if you are good to go, you can look into courses for courses in Udemy and Coursera. R is better for bioinformatics students as Python does not teach core coding. Okay, that is uh, an assumption. Okay, so I wouldn't consider that way, because I had worked both with R and Python, and yeah, R is more sound in statistics part, and Python is more sound in visualization part. If you are doing an experiment or a study which concentrates more on visualizing, which concentrates more on image analysis, then good to go with Python. And if you want to relate, if you want to work with statistics behind each and every biological data, biological information, then yeah, R is a better option than Python, because it will make things simpler. It is not that Python cannot do, it will make things simpler. Any resource or online materials for chip-seq analysis? Okay, I think I can give you that. Just a second. What's this for basic R strips? Yeah, thank you, Arun, for that. So I'll get the chipsy analysis part. So actually this one was a video which we referred in our college days, and yeah, to start with chipseq analysis, this is a really good video to watch. So go with these two videos, the top two videos I'm showing, chipseq analysis and step-by-step guide. So this will highlight it will become a basic guide how to start with chipseq data analysis. And then I would always suggest not to go by book. Once you like try with some already given data source, just try to dig down yourself. So I mean, but these two videos. So wait, I'll try to share the link. Address. What is this? And the other one is this. Maybe in future I'll find some person of this expertise to organize a demonstration on chipseq data analysis. That would help you. So I'll keep you posted. Yeah. Wait a minute. I have posted that to one particular person. Sorry. Copy and everyone. Okay, so these are the two links. So yeah, go through this if you are fond of chip-seq analysis. And so yeah, good to go. So the very next important part of any PDB ID is taking the FASTA sequence, downloading it in a FASTA format or downloading it in a PDB format. So what does this PDB format do? Protein data bank format. So this format has all the structural information of the particular protein which is reported. Fine, so let's first display. So you can see it in some kind of format, some kind of alignment, some kind of arrangement of data, different data, right? So there are remarks, there are sequenced residues. You can have hetero atoms, you can have helix here, you have sheets here, then you have links. Links in the sense, basically these are some kind of structures which which do not fall under helix, which do not satisfy sheets, and yeah, you have these. So you have the atoms, number of atoms, all the structural details. Why is this in format? I mean, why is this in this format? So to answer that, we will download it in a PDB format. Yeah, okay, so I already have a downloaded one, so that's why it's getting one. And we will try to visualize this PDB doing nothing directly. Uh, just a minute. Yeah. Okay, I would just stop sharing for a moment. Just wait, just hold on. Why we only use PDB format for downloading? Yeah, I'll get back to you that. Just a minute, just a minute. I'll just get back. So we will be looking at the primal visualization. So we are going to start with visualizing with primal. Yeah, and I have launched the application. Can we start this by tomorrow? Uh, yeah, just can you just spare me 5 more minutes? I'll just show this and we'll start the. I have another concept. We'll start that by tomorrow. Just a small concept, and we'll continue with this tomorrow. Yeah, I'll just touch this. So you see, you can get PDB directly, right here. So before that, I would like to open the downloaded file. So which is in downloads. Yeah. So yeah, right. So I have got the structure which I can visualize. This is the 3D structure which I can visualize. So I can display the sequence here. So I went display and I have the sequence here. I can know what exactly. So I have the 260 sequence, and apart from that I have two ligands, and then these are just solvents. So these are water molecules, or these are the ions, the solvents which have been there here. Yeah, you see this red part, right? All these. So this is what is the visualization. I don't want to go deeper into the visualizing part now because yeah, it's time already. So I would do one thing. I would delete the fragment. Yeah. So I'll action. I'll delete the object. So I have nothing here, and I can directly fetch any PDB. It is not that I need to download a PDB to my system, to my computer, and always run it on visualization software. No. So I am going to fetch one HED directly. Okay, I'll fetch some other thing because one HED is already in my computer. So fine, I'll fetch some other PDB ID. One second. We'll just search for a kinase, and we'll just note the name. We'll find that randomly. I just want to do this randomly to make sure that that particular thing works. So 3HQP. Yeah, I have no idea. I did not download this. So going to primal, fetch 3HQP. All I need is just the internet connection, and okay, so connection very poor. All right, big molecule. Yeah, I got it. So since it's a big molecule, it took time. It's a big structure, right? So I got the structure. So just you need not always download every PDB structure here. So once I got the structure, I can save this as a PDB file. So I can save this as a PDB. I can save this structure as a PDB file, and automatically my PDB details, as we saw earlier, will be generated in all those arrangements and alignments. So this is the kickstart of PDB and the structures, retrieving sequences, retrieving structures, retrieving data, all that. So hopefully we will be continuing with again looking into visualizing things. We will be continuing with visualization to some extent, not very deeply. Then we need to kickstart BLAST. So we will be looking into alignment. So BLAST is basically basic local alignment search tool. So we will be looking into the alignment part, and then you will have people to explain you homology modeling, mutagenesis, and the further hands-on concepts. So hopefully we'll try to cover things, yeah, but not to hastily cover things. If at all we miss something, we'll always get a better takeaway of the previous things, right? So we'll have a mutual understanding on that. Be okay. So like Rasmol, Pymol need not be installed. I have it installed. I have it. I have Pymol installed. I have Pymol installed. I need not have the PDB installed. That is what I was downloaded. That is what I was trying to state. We use PDB format for visualizing or for doing further analysis, as it has all of the information about the protein. In FASTA format, you can see there's only amino acid sequence. Moreover, visualizing tools support PDB format. So okay, so you have given a sort of explanation. Yeah, but I'll tell you. You again, it depends on what a person desires to. I am a person who is more into structural bioinformatics. I am interested in the structure of the protein. Yeah, PDB is going to help me. But if I'm a person who is into the functions, who is more into the molecular arrangement of the protein, I need not worry too much about the structure. I can go better with the sequence, because I am just looking around what is the similarity or what is the dissimilarity between the sequences. Why is this there? Why is this not there? So again, everything has its own advantage. It is just the purpose you are using it to. Yeah, so I would call it a session.